Okay, hello everyone. I'm very glad to be here. I, of course, want to thank the other organizers for inviting me. This presentation I'm going to give you is a little bit off the topic from the very center topic of the school. It was meant to be a sort of opening subject. Okay, so because of the planification of the week, somehow my talk bounced on Monday, but. So yeah, so it's going to be quite exotic for your community, I guess. So I'm going to talk to you about hybrid optomechanics for quantum sensing, and mostly the focus will be on this kind of material, which are crystals. So first, what is a quantum sensor? A quantum sensor is only, I mean, it's quite simple. It doesn't have to be very complicated. It's a sensor that utilizes properties of quantum mechanics to beat the limits of a given sensor technology. So these quantum properties that the quantum sensor is going to be based on can be either quantum superposition states, but can be also more complex quantum mechanic properties, such as squeeze states or entanglement, and also can rely on single photons, so quantum states of the electromagnetic field. Just two examples to illustrate this concept. As you know, we have large interferometers that are capturing gravitational waves around the world. And for example, LIGO has implemented recently squeezed light into the interferometer that allows us to go beyond the standard quantum limit thanks to this very quantum mechanical property of light. The second example is NV centers for magnetometry. So NV centers are artificial atoms in a solid state matrix. And they are very sensitive to magnetic field, and so the fact that the sensitivity to magnetic field is the Zeeman effect, and is a quantum mechanics property. The essential ingredient for this quantum sensing is the coupling. The coupling between the quantum systems that you use as a probe and the quantity you want to measure. And one example of such a coupling is optomechanical coupling. So what I mean by optomechanical coupling is the coupling between a mechanical degree of freedom, for example, an object that moves, whatever it is. It can be, for example, a mechanical resonator, but is not limited to that. And the other degree of freedom that we want to couple this mechanical degree of freedom with is a quantum degree of freedom, for example, a two-level system. But also, it's not limited to exactly a two-level system. And of course, optomechanical systems are natural quantum sensors for sensing stress or motion. Because exactly as I told you in the last slide, we are going to use the quantum properties of this side of the coupling to probe the mechanical degree of freedom. There is a little subtlety to optomechanics, which is hybrid. Sorry, I have an example first for optomechanics. It's let's say the original optomechanical system that has been explored is optical cavities. An optical cavity is an intrinsically optomechanical system because the field inside the cavity is your quantum degree of freedom, because you can have quantum states of the field, and it's intrinsically coupled to the mechanical modes of the mirrors, because of course if the mirror moves, then the electromagnetic field in the cavity will get a phase shift, and so you have this optomechanical coupling that is provided by this configuration here. Now, when people talk about hybrid optomechanics, it's a little bit more specific. It's when the two degrees of freedom are contained into the same object. That's all it means. So it's just one single object that has these 2 degrees of freedom within it. And one example is, for example, so sometimes they actually have to be assembled together, these 2 degrees of freedom. And this is the case here, where a quantum dot is inserted at the basis of a semiconductor micropillar. So you have here, this is like, I don't know, 10 microns long pillar. And this has the possibility to oscillate like this. So it's your mechanical resonator. And it's coupled to the quantum state of the quantum dot that is at the basis of this object. and the quantum dot is also an artificial atom, so it has a sort of two-level-like structure. So what I'm going to talk to you about is an example of hybrid optomechanics. I must go back to the beginning, which is the exact materials we're going to talk about today. So what I'm dealing with is rare earth ion-doped crystals. These crystals are transparent. When you look at them, they look transparent. It's quite boring, actually, as an object. Okay, it's just a cuboid. But actually, it has been prepared in a very specific manner, so that some impurities, and very specific impurities, are inserted into this matrix. And these impurities are chosen amongst the rare earths, which are actually the lanthanides here. Okay, and these species are very specific because they have a particular electronic configuration. The electronic orbitals that interact with light are the 4f electrons, and they are actually in a sort of inner position within the atomic configuration, whereas 5s and 5p layers do not interact with light, and they are more external, which means that the electrons that are going to interact with light are protected from whatever happens around them due to this shielding. And this is actually very, very interesting, because you can then put these ions inside a solid, so with many ions around them, many objects around them, and still have some sort of dilute medium property, although it's a condensed matter object. So as an example, well, usually, so first, of course, you have to cool them down, otherwise you don't see any coherence at all. So if you cool them down below 4 Kelvin, you get exceptionally narrow lines. When I say exceptionally narrow, I want to compare to ordinary solid states. Okay, so the order of magnitude of the lines, of the atomic lines that you can observe in these materials are below the 100 kilohertz, and it can even go down to 100 hertz. So it's ensembles of ultra-coherent quantum systems that can be well, we can define the width of this atomic line, of atomic resonance, with a homogeneous width, which is around 10 kilohertz, or something around this order of magnitude. But of course, as I told you, it's condensed matter. The ions are surrounded, yes, it's a dilute medium, but it's also condensed matter. The ions are surrounded by a lot of things, ions, defects, everything. And so, although this line is narrow, it's actually going to be disturbed by the environment to a certain extent, which is why the collective absorption of the whole crystal, like this, is actually the sum of many individual homogeneous lines which are slightly shifted with respect to one another. And this leads to an inhomogeneous broadening, so it's like a Doppler broadening, but it's static. Okay, so each of these lines corresponds to a different environment within the crystal matrix. So what you get is, when you don't do anything special, you just cool down the sample, you get an absorption line which is quite broad, around gigahertz wide, but you know that it's consisting of a very large quantity of very narrow lines with a kilohertz range width. And so how can one actually go back, well, retrieve this homogeneous width? Well, we can use a tool which is called spectral hole burning. This is a tool which works in the following way. You shine a narrow laser within the absorption line of the crystal, and this laser is going to address only the ions that are resonant with the field. Okay, and it's going to leave all the other ones alone. It's not going to interact with them. So what's going to happen is that the resonant ions are going to get promoted to a different atomic level, and they're not going to be able to absorb anymore. Which is why after they can stay in this state for a few milliseconds, maybe more, depending on the systems. So after this, if you scan the absorption profile again, then you will see a hole that has been created within the absorption profile. So this is called spectral hole burning. It's a very useful spectroscopic tool because it can actually help you retrieve this gamma H property, this quantity. You can actually measure it this way. But it's also a way to retrieve the coherent properties of the system, because of course the homogeneous width is the inverse of the lifetime of the coherent superposition that you can create in such a system. So another, an interesting thing about spectral hole burning is that it gives you a programmable absorption profile that lasts a couple of milliseconds, maybe more, with a lifetime around millisecond and resolution kilohertz. So the applications of such devices, such objects, are quite many actually. It ranges over a wide panorama of applications, and the first one in the early years of rarefied spectroscopy, it was optical storage, but that was before the compact disc came in, and then people realized that cryogenic operation was a little bit a problem. So this has been ditched now. It's okay. No, optical storage is not considered anymore. But then you have, yes, another application which is actually being under important developments is radio frequency signal processing. So in the last edition of Cargèse School, you had a talk about this, if I'm correct. And there's also applications in medical imaging. I won't have time to talk about this today. And there are also many applications in quantum technologies, including quantum computers, quantum networks, and of course quantum sensors, which will be the topic of today. And all these applications rely on this narrow single ion width, okay, homogeneous width. So now let's back to optomechanics. Let's go back to optomechanics. It's actually been known since the 1960s that rare-earth-ion doped crystals are sensitive to pressure. You can find in this in this Russian paper. So if you can find the English version, I would be interested. But okay, I have the title, but I think that's almost all I can get. So as you can see in this nice animation, when you press on the crystal, the line shifts. This is very well known, and it has been used for a while to understand the mechanical properties of the crystals. So there is this is our optomechanical coupling that we're going to build a quantum sensor on. So we have this sensitivity to stress. So we know that stress induces a line shift, and we have well, not we, but it's been known for a while that this effect is linear, at least in the limit of elasticity of the crystal. So if you just look at the broadband absorption line of a rare-earth doped crystal, and you press on this crystal, you will see a line shift. But if this line is broad, you will need a large pressure to see an effect. Okay, so let's just look at the orders of magnitude. Let's take, for example, the example of thulium-YAG, which has a Young's modulus of 300 gigapascal and sensitivity to stress of around 70 hertz per pascal. Well, in order to move the line by 20 gigahertz, you need 300 megapascal. So this is the order of magnitude of pressure that people needed in order to see this effect in the early times, because they were just looking at these broad lines here, and they didn't have narrow lasers and etc. But now we are able to perform spectral hole burning with a narrow resolution. So for example, in thulium-YAG, it's quite easy to get 100 kilohertz spectral holes. So now if you want to see how much stress you need to shift the line by its width, or more or less, if you want to shift it by 100 kilohertz, well, it's just a proportionality equation. You get sensitivity to stress of around 1.5 kilopascal. So this spectral hole burning capacity gives you a much better sensitivity. Okay. And another example, which I find is very striking, is europium YSO, which is actually one of the best rare-earth-ion doped crystals in some respect, depending on the applications, because you have a lot of ions that you can dope in a lot of matrices. So there's a broad choice of systems that you can work on. And this one is very interesting because they have similar Young modulus and sensitivity to stress, but the spectral holes that you can burn in them is like a couple of kilohertz. So you get extreme sensitivity to stress. Okay, and this is a nice example of the shifts of a spectral hole that has been measured by our colleagues at CIRT. Okay, so this sensitivity to stress is great because we can make a quantum sensor about it. But actually, in the first place, it was considered as a huge problem. Why? Because for a while, people in this rarefied crystal community have been working with liquid helium cryostats. And as you may know, these kind of devices, they have quite large cooling power, so it's easy to well, of course you need to get the helium in the lab, but once you have the helium, it's very convenient because it's just cold and it just works by itself pretty much, and it has low vibration. However, for the past 15 years now, the helium shortage has been increasing a lot. There have been periodic shortages every 2 years or something, and at some point the price has risen so much that it has reached the price of champagne. So I let you imagine if we would like to drink so much champagne in the lab. Anyway, but okay, so there has been a lot of progress on closed cycle machines that replace these devices. So they replace them, but they are not quite the same. They are kind of high power fridges, pretty much, with a compressor and a fluid, which is this time helium instead of freon in your fridge or something like this. But so they have a couple of drawbacks, which are low cooling power and high level of vibrations, because as every fridge you have something that vibrates. You have a rotating valve and things like this, so the sample vibrates. And this is actually a huge problem, because when your sample is sitting on a vibrating plate, well, then the lines will shift in synchrony with the vibrations, of course, as we have seen earlier. So for every applications that relies on rarefied crystals, and of course relying on closed cycle cryostats, which is unavoidable right now because of this helium shortage, we are subject to this vibration-induced decoherence. So this line that moves uncontrollably. But actually, so we after observing this big problem, we thought maybe let's turn this into an advantage and make a sensor out of it. Because of course, when you're sensitive to something, then it's the moment to make a sensor. So and it's actually going to be a quantum sensor, because it's going to be really based on these narrow lines that are connected to these quantum superposition states in our rarefied crystals. So detecting vibrations using this sensitivity to the stress, which is called the piezospectroscopic effect, is going to work in the following way. We consider a crystal that is lying on a vibrating plate, and vibrating plate means vibrations propagating into the volume of the crystal. And this means that inside the volume of the crystal you have inhomogeneous strain, which means that the beam that goes through the crystal there will probe different parts of the crystal, and will probe parts with different stress. So it will actually the spectral hole that you will probe in this crystal is going to be broadened, because the strain is not homogeneous along the whole path of the light. And the hypothesis that we can make is that when the vibration passes through, when a mechanical wave passes through a crystal where there is a spectral hole burned, this mechanical wave doesn't change the number of atoms that have been optically pumped into a spectral hole. So the hole is going to keep its area. Okay. So we are just going to probe the center of the hole, and if the hole gets broader because of stress, then the absorption is going to go up because it's the product of the height of the hole and the width of the hole is going to be constant. Okay. So we don't have to measure the whole shape of the hole. We just have to measure the absorption at the center, and we get sort of time-dependent stress that propagates here. So there is a little math, which is not so interesting, but just to understand how we relate the velocity of the plate with the broadening of the hole, and this whole area conservation that we assume, and then we can measure the absorption just by looking at the transmitted beam using what all of you know as the Berlambert law, but I call it the Bouguer law because he discovered it first. So if you want to look it up. Some people call it the Berlambert-Bouguer law, but well, maybe you just get this guy out of the oblivion. Yeah. Okay, so we have a very simple real-time readout of the velocity of the plate using this spectral Hall bending in the volume of the crystal. So we try to implement this idea in a pulse tube cryostat, and it was actually a cryostat that vibrated a lot. It was actually kind of intentional. We had this pulse tube cryostat, and we just stuck the crystal on the second stage, and it's like well, okay. The one thing that people maybe don't imagine is that when you buy a cryostat like this, no one tells you how much it vibrates in reality. Okay, so well, you just stick your crystal to the cold plate and look what happens. And so we performed this continuous interrogation of the spectral Hall, and observed that the transmission was very noisy. So this is not exactly the transmission. It's already converted. It's a transmission converted into the spectral Hall width as a function of time. And we plot it against the acoustic noise that we record in the room. Okay, and you can hear, you can recognize very nicely, I think, if you know cryostats, the very soft sound of cryostat that goes chi chu like this, chi chu, yes. And so, and I mean, it's okay. So it's very correlated, and so we thought, well, let's do the spectral analysis of this signal, and we can observe that depending on the moments in the cycle. So when it's blue, it's the beginning of the cycle, and it goes all the way through the rainbow, all the way to orange, which is the noise at the end of a cycle. So it goes from blue here, all the way through green and yellow up to orange there, and then back. And we can see that the spectrum of the displacement in meter per square root of hertz for metrologists, they like this unit, yes. We can see that there are a lot of high frequencies, which are some are correlated with a position in the spectrum, some are not too much. So yes, there is a lot of noise, and now we wanted to know whether this was really correlated to the acoustic noise effectively, and maybe not the laser or something like this. So we modified the cryostat, and we inserted a gas chamber inside the cryostat. So instead of sticking the crystal on the second stage directly, we suspended the crystal. Well, we stuck the crystal on a sort of a sample holder in copper like this, and then suspended this sample holder in a gas of helium. And the idea of this suspension is that we're going to completely decouple the vibrations from the second stage. They're not going to propagate all the way to the crystal, or at least not in an efficient way. But still, we have a good conduction of heat. So a correct cooling power by using gas inside this chamber. And this is the displacement spectra that we obtained, and we can see that these in blue you have the sample when it's stuck on the cold finger, as in average over the whole cycles. And then when you suspend the crystal, you get the yellow and the red curve. And we observe that this, so you can see that all these peaks actually vanish. So it's really correlated to the acoustic perturbations inside the cryostat. And we observed that it was we had a sort of baseline which was related to the frequency noise of our laser. So we're currently going down on these limits. What is very interesting in this picture is that we, just for the sake of comparison, we wanted to plot the limit of sensitivity of an interferometric measurement based on a simple Fabry-Perot cavity, where you put a mirror inside the crystal and a mirror outside, and you can measure the displacement by exploring the change in the cavity resonances, but using the same optical power. And as you can see, this is the magenta line here. This is the limit. Oops, yes, the limit of sensitivity, shot noise limited sensitivity of an interferometric setup with the same optical power as we use in this setup. So you can see that at 1 megahertz we gain like at least 3 orders of magnitude. Okay, so this what I have presented to you is a very sensitive vibration sensing at cryogenic temperature. So is it useful? Well, I haven't really talked about this right now. And so first, it's very simple because you just need a monochromatic laser at the right wavelength and with decent line width. You need a rare earth doped crystal, and you need a photodetector. It's very, very basic, really. And if we want to compare it to other solutions that exist for vibration sensing, let's look at accelerometers, for example. So if you want to use an accelerometer inside a cryostat to work at low temperature, you're going to run into some problems because so of course the detection bandwidth is not very high, and at low temperature the accelerometers get worse and worse because the piezo electrical coefficients just vanish pretty much, and they have the defect of adding a lot of mass into the device, which you have to cool down, of course, and it's not very convenient. Optical methods are a little bit better because they are contactless, so to say, because you just need to stick a little mirror somewhere. It doesn't have to be heavy. They are broadband because the detectors are broadband. However, they are non-inertial, which means that you actually measure a displacement with respect to a reference point, which can itself not be quite stable. And ideally, when one wants to characterize vibrations in a given device, you want to characterize the vibrations with respect to like a Galilean referential. So you really want an inertial measurement. And so the good thing is that our idea has all these good properties. It is both contactless, large bandwidth. It allows an inertial measurement and with a large sensitivity at low temperature. And actually doesn't work at all at room temperature, but yeah, you have other solutions for that. There are some perspectives for ultrasensitive vibration sensing, because actually now we have started to understand how vibrations couple to the crystals we have, and I'm talking about this as with my history of a spectroscopist of these such crystals, and we are very interested in knowing how we can actually engineer the crystals so that it's going to be more or less sensitive to vibrations depending on what we want to do. And of course, important factors are the mechanical quality of the object in order to know how the waves are propagating inside this object. So these crystals are generally single crystals, so really millimetric single crystal all the way, with high quality and very clean surfaces with optical polishing, everything. So in principle, they should lead to quite high mechanical Q factors, and they are quite easy to shape with saws and polishing devices, so that you can actually create many sizes, many geometries. So using bulk crystals actually gives you a sensitivity to quite low frequencies, so pretty much below 100 kilohertz. So as an example, 100 kilohertz is the eigenfrequency of the first order flexural mode of a 10 millimeter plate cantilever in such crystals. But then you have quite a large technical noise, such as frequency noise, that ran into play. But if you can also use micro cantilevers like this. This one is 100 microns long, made of rare earth doped crystals. This is made at Institut in Grenoble. So these devices have much larger eigenfrequencies, but they are more sensitive to thermal noise. So depending on what we want to do, we might want to adapt the design. It's also very important to understand how this sensor is going to be limited in terms of sensitivity by both fundamental and technical problems. So one first thing to do is that, as I told you in the beginning, we are actually measuring the absorption at the center of the hole. And this means that for small fluctuations, we are actually not sensitive at all, right? Because it's a quadratic function. So it's really not optimal at all. So we want to go to the side of the hole, which requires a little care, because of course if you probe the side of the hole, you will burn a hole at the side. So you will actually distort the shape of the hole. So you need a little work on this. You can also try to reduce the laser frequency noise and try to go towards identifying fundamental limitations such as thermal noise due to thermal motion and the frequency cutoffs. So one example of applications of this quantum sensor is, as I told you, so characterizing cryostats pretty much. And when you can characterize a cryostat in terms of vibrations, you can determine how the plate moves, then you will actually be able to perform some retroaction, some feedback on the crystal, on the cryostat cold plate. And this is a huge goal for the whole cryogenic-based applications, because a lot of cryogenic research topics rely on cryostats. They are sensitive to vibrations, and it's especially the examples of AFM microscopy, where you have a cantilever that is approached very close to a sample, and when you want to measure the shape of or the density of something on a surface. Well, if the object on which the cantilever is attached is vibrating, well, then you are really in trouble because you might crash the tip on your sample. So actually, so up to now, let's see, where am I? On en est où? Il y a 18 minutes. Perfect. So up to now, I've been talking about sensing, really. And I wanted to talk to you about the sort of hidden side of piezospectroscopic effect. So what I call hidden side is actually considering that we have this optomechanical coupling into in these rare earth-ion doped crystals. So the stress leads to a line shift due to this piezospectroscopic effect. And inside this optomechanical concept, as you see here, I have a double-sided arrow, which means that there must be a reverse effect. Okay. And this reverse effect, we can look at it from this perspective. Exciting the quantum degree of freedom should, in principle, impact the mechanical degree of freedom. So we should be able, by exciting the two-level system, be able to make motion at some point. Okay. This can be termed as back action because it's really let's see. It comes from the quantum mechanics paradigm of back action, really. As soon as you have a coupling in a way, you have a back action in the reverse way. So we have tried to investigate this in the past few years, which was actually a quite exciting journey. And nothing's happening. Ta-da! Why not? So one way to look at this back action phenomenon is to consider that exciting a rare earth ion inside the crystalline matrix will actually lead to a change of shape of its electronic orbital. So if you have all seen this kind of graph of a table where you have the shape, the actual geometric shape of the electronic orbitals of various electronic states. And you see that if you change just one parameter in whatever direction, you will have a strong change of shape. And in our case, it shouldn't be different, right? When we excite the rare earth ions from one level to the other, we will have a change of shape because we are changing, we are promoting the atoms into a different electronic orbital within the 4F layer, but still within a different orbital. So in rare earth ion doped crystals, the way we see things is that optical excitation is going to modify the electronic wave function. The ion, so the global ion shape is going to change slightly. I'm not saying it's going to be a huge effect. Huh? Don't get me wrong. And then once the ion shape has changed, well, then it has to find its place somehow within the matrix. So it pushes the ions around it, right? It has a solid matrix all around it. But if you really have to get a different electronic orbital, then it's going to push. So what we try to do is to actually measure the distortion of this crystal, right? And we term this piezo orbital back action so in reference to piezo as stress and orbital as orbital, yes. how can one measure this? Well, first we need to consider the orders of magnitude. So the typical relative ionic radius change when you excite the atom from one level to the optically excited one, just theoretical considerations give you a ratio of 1% change in the radius. It's very small, and it's so small. I mean, 1% is not very small for a physicist. You all can measure 1% of something, I think. But nevertheless, the problem is that it's actually a dilute medium. You have just one rare earth ion every. I mean, the density is not very high in these materials, so the effect on the crystal is really going to be small. So one thing we can do is to enhance this effect by using a large number of identical atoms, and we are going to try to push this number of identical atoms to the maximum that we can do. So for this. To measure this, we first try to see what has been done before in similar systems. So, for example, these quantum dots at the basis of a microresonator. Well, they actually tried to observe such an effect, and they relied on the fact that the mechanical degree of freedom of their object has a quite definite mode with the flexural mode of the pillar like this, and so if you can actually excite your ion and excite the mechanical the eigen mode of your oscillator, you will have a strong effect. You address really the movement at mechanical resonance. But the price to pay is that they had a very low number of atoms. They actually had just one quantum system, okay, one quantum dot at the basis of the pillar. In our approach, since we have already bulk objects and it's not easy to have a single ion anywhere, we decided that let's use the bulk capacity of our objects, because it will give us a large number of atoms, which will in fact be actually limited by the beam size, but that's okay. It's still going to be quite big. But there will be no mechanical resonances, at least at the time scales that we are looking at. But since you have no resonances, then you have no, you have a quite spectrally flat response. The transfer function of the motion is going to be quite flat, which means that you can actually perform a time resolve study. So let's see. We resorted to this geometry. So we shine a laser from inside this square, which is 1 centimeter by 1 centimeter square, and it's 4 millimeters thick. We shine a laser through this crystal close to a surface, and what we want to do is to measure the surface distortion, and the surface that is going to be distorted is the one that is close to the pump beam. And we are measuring this distortion by using a probe beam that is reflected on this surface. The other trick that we use is that we actually thought, well, this phenomenon that we want to observe, this piezo-orbital back action, it's a very fundamental effect. It's not going to be only visible at cryogenic temperature. It's going to be visible at every temperature, because it's the wave function of the orbitals. So we decided to work at room temperature. And at room temperature, all the ions are identical, because the homogeneous width that I mentioned earlier, the narrow lines, they actually get so broad that you don't see the inhomogeneous broadening anymore. So all the ions are identical. So yeah, this is another view of the setup. Okay, we used the level structure of thulium YAG, which is an ion I've been working on for a while now. And the principle is going to be like this. We're going to excite the ions from the ground state, promote them to some excited state where they are going to stay for a little bit less than a millisecond. Then they will relax to a long-lived state, around 7 milliseconds, and then relax to the ground state. And following this population transfer, we expect to see some mechanical effects due to this displacement in several states. So just looking at rate equations for the populations, we estimate that we are at some point after 3 milliseconds optical pumping, we are going to have 65% of the ions within the laser volume. They are going to be in a different atomic state than the ground state. So we're going to have a massive population transfer. And if you count the number of atoms yes, okay. If you count the number of atoms inside the laser beam, given the density, the volumic density of ions, we're going to have 4×10⁻14 identical thulium ions, all in the same state, transferred to a different atomic state. So this is going to be our enhancement factor that we were looking for. So we were looking for a very small effect, but we magnify it by 4×10⁻14. And as you will see, it's not, well, the overall effect is still quite small. Okay. So we tried to do this experiment by shining so we shine the pump beam on the side of the crystal and have this probe beam on the side. And if we put the probe beam quite close to the expected bump center, we see an angle, a surface, so an angle of deflection of the beam, which looks this way. So it goes up for 3 milliseconds and then goes down, with a lifetime that really looks like the lifetime of the state where we're looking for something. So it's very encouraging. Well, okay, it's just 3 microradians. It's not a huge tilt, but it's really detectable if you average enough. And it really looks like the evolution of the metastable state. However, if you put your probe beam a little further away, without changing anything to the excitation sequence, you just move the probe beam a little further away, what you see is something which is very different. You have this blue curve here that slowly goes up, so it goes up a little bit less than the 3 microradians one. But the important part is that it's actually a delayed response. And this means this is actually more indicating a thermal effect rather than a piezo-orbital effect. Because, of course, we expect that there will be some heating inside the crystal when you do such an experiment. When you shine a laser into an absorptive material, of course it's going to be it's going to heat up, and if it heats up, then there is a thermal expansion. So, in order to see whether it's photothermal or piezo-orbital, or maybe a little bit of both, we performed some verifications. First, we wanted to look whether this photothermal, whether this back action whether the signal was resonant or not in wavelength. So we actually detuned our pumping laser along the multiple line profile of thulium YAG, which is very well known, and we plot here just the top of this curve here for different wavelengths, and you can see that it closely follows the absorption profile of thulium YAG. So yes, the deflection signal is resonant, but this doesn't prove that it's not photothermal. It just proves that the motion that we see, because so there is a motion, we know there is a motion, but this result here just proves that this effect is just connected with the atomic dynamics, and it's not connected with defects or imperfection of the crystal, for example. What we had to do now, it was actually the most difficult part of this work, was to be able to differentiate these two effects while knowing that they are both resonant. So we actually made this constatation that the piezo-orbital effect, we think, by definition, it has to be an instantaneous effect, and of course a local effect. So it cannot propagate to a different location. I mean, it's just the ion that is excited that gets expanded somehow, and then when it relaxes, it just goes back to its initial size. Whereas the photothermal effect is going to obey the heat diffusion phenomena. Okay, so we could actually we know that we can differentiate these two effects by their spatial-temporal behavior. So we did this deflection measurement for many positions of the probe beam, and we obtained this kind of curve there. And you see that, so close to the center you have this sharp increase and then slow relaxation, and far from the center you have this delayed actuation that I showed you earlier. Only this time, since you have many points, then you can really reconstruct even the shape of the bump in the crystal surface. And then we modeled the piezo-orbital and photothermal effect both in time and space. And so for piezo-orbital, this was kind of a very simple simulation, because we don't know anything about it pretty much. And then, so we had to make simple assumptions, right? You cannot do anything complicated. And for photothermal effect, we performed a simulation that was more complex because we actually know everything about photothermal. We know exactly how heat builds up in these systems. We know it exactly because we have, so as you can see, I like old papers, 1975 publication for laser crystals. And in this specific crystal, you can find all the relaxation rates, non-radiative, radiative, cross-relaxation, everything. You can find all the rates, and this actually gives you the phonon heat load over time. So it means that knowing that you shine your crystal with a square laser pulse, you can derive the heat load associated to each of the relaxations. So for example, E2H is the excited state towards the H state. This gives you some source of heat with a very specific time dependence, because it depends on how this state gets filled up and then empties somehow. So each of these canals of relaxation gives you a source of heat, and then you can just add everything up, and you know how much heat you will generate within the crystal as a function of time. Then you plug this into the heat equation, and you get the temperature distribution from which you derive the expansion of the crystal as a function of position and time. And you get the deflection angle, the theoretical deflection angle associated to photothermal effect. So we have this piezo-orbital fact part, which, so I told you we don't know anything about. We just know one thing, is that it's completely correlated with, it has to be proportional to the number of atoms inside the metastable state, which is the long-lived state that we have in our system. And we have this photothermal part, which is completely imposed by the model with the heat diffusion and everything. So we put everything together and fit the results with this. And we actually, we fit the results very well and observe that the photothermal effect is completely, is actually alone the only effect at a distance, which we actually suspected because it's really typical of a thermal effect with this delayed actuation. Yes, I'm stopping. And the piezo-orbital effect is present more in the center. So just to go a little bit further away, yes. So our demonstration of piezo-orbital effect showed that we generate a force pushing the crystal surface towards the outside by 0.3 Newton. So if you're not familiar with optomechanics, this might seem small, but it's actually huge. Yeah, okay. Okay, because you can compare it to quantum dots, where you have really much smaller values. Okay, so maybe I'll stop there. I have told you a lot of. I'll just shift. I told you a lot about optomechanical coupling into these systems. They are mostly based on. So they are. Everything I told you is really based on the coherence of these systems, which is coming from the electronic structure of the ions and the spectral hole bonding capacity. I have shown you how you can use the piezospectroscopic effect to do more or less applied research, such as vibration sensing, accelerometry, and maybe help for quantum technologies as a whole, by making nice enabling technologies. And I have also told you about piezo-orbital effect, which is a very fundamental effect, and that we might use for other fundamental aspects that I didn't really have time to tell you about. And this is the end. I want to thank all my collaborators and you for your attention. Thank you.